The next two tests that we're going to take a look at are called the ratio and the root test. And they're super useful tests because they test not just for convergence, but we're actually testing for absolute convergence. So it's a very strong type of convergence that we're getting out of these two tests. So with the ratio and the root test, we define either a ratio of terms, so we take the limit as k is approaching infinity of the a sub k plus 1 term over the a sub k term. But because we're taking this limit, and it is often that our terms in our series are themselves fractions or ratios, it actually makes a little more sense to maybe write the ratio test in this form. We take the a sub k plus 1 term over 1 times the reciprocal of the a sub k term. Now, the root test is very similar. We take the absolute value of the terms, but instead of taking a ratio of terms, we take the kth root of the terms. And once again, it is often a little easier to think of that limit in this form, the absolute value of the terms, and then we take the 1 over k. We use the fractional form of the root rather than the root, the 1 over k, as an exponent, and apply that. Now, this is what these two tests give us. When we take that limit, if that limit value, that L, is less than 1, then the series itself is converging absolutely. So again, very strong convergence if we get a limit of a ratio or a root of the terms, if we get a limit that is less than 1. Now, if the limit is greater than 1, which includes infinity, if it isn't infinite, if it is growing without bound, then, and it will only be approaching positive infinity because we're taking the absolute value. So if it is greater than 1, then the terms, the series is divergent. If L happens to be equal to 1, this is the one place where we get an inconclusive result, and you have to go back to some other method. In that scenario, you come back, and we have all of our other tests from the previous section. So if the ratio or the root test is inconclusive, we just go back to the original and we try something else. Okay, let's look at some examples. All right, so just a quick reminder that we are discussing convergence, and when we do, from here on out, actually starting with the previous section with the alternating series test, we want to define the convergence as either absolute convergence or conditional convergence. So remember, absolute convergence is the strongest type of convergence, meaning that the absolute value of the terms, regardless of if there's a switch or signs changing, that the absolute value of the terms, when we take the absolute value of the terms, the series of the absolute value of the terms is convergence, very strong convergence, versus that conditional convergence, which says that the series is convergent, but if you take the absolute value, it is divergent. So quick reminder, the ratio and the root test are giving us absolute, that very, very strong type of convergence if we get a result out of the root or the ratio test. Okay. So let's take a look at a couple examples. So let's determine if the following series converge absolutely, converge conditionally, or diverge. So we're looking at this series and we're going to try the ratio test on it. So remember, with the ratio test, what we want to do is we're going to define the limit, and on the next few I'll just jump right into it, but we're going to take the limit as k is approaching infinity. Oh, actually it's n. So it's as n approaches infinity. I just looked back at my series and it was approaching infinity. It is n approaching infinity because the index is n, not k. So as n approaches infinity, and what we're going to do is we're going to take the ratio of the a sub n plus 1 term over the a sub n. But it is often a little easier to think of this as the a sub n plus 1 term over 1. So plug in n plus 1 for the index, and then multiply by the reciprocal of 1 over a sub n. And we're taking the absolute value of that ratio and taking the limit as n goes to infinity. So let's see what happens. So if we define L to be the limit as n approaches infinity, now when I plug in n plus 1, I get negative 10 to the n plus 1, and I'll write out all the algebra here on these first couple. 4 to the, got a squiggle there, 4 to the 2 times n plus 1 in the power there, and then n plus 1 plus 1. So we're replacing each of the n's, right? We're plugging in n plus 1 for the n plus 1 term. All right, times 1 over, or the reciprocal. When you say 1 over, of course, this indicates the reciprocal of the a sub nth term. So the reciprocal of the a sub nth term, we just flip it, and this becomes 4 to the 2n plus 1 on the top times n plus 1, and on the bottom, negative 10 to the nth. And we're taking that in absolute value. Now we want to get that all nice and simplified. And so what I'm going to do is I'm sort of going to group in fractions each of the kind of similar factors so that I can see what's going to cancel. So the limit is n is approaching infinity. I'm going to put the negative 10s together. So I got negative 10 to the n plus 1. And in the denominator, I have a negative 10 to the n. Now you don't have to do this. I'm just going to do this on this first one so we can see the similarities in the canceling. We've got 4 raised to the 2n plus 1 in the numerator. And in the denominator, we have 4 to the, well, that actually right there becomes, because we distribute the 2, so we get 2n plus 2 plus 1, so we get 2n plus 3 on the denominator of the denominator factor of 4. So 4 to the 2n plus 3. And then we're multiplying by n plus 1 and n plus 2 because we combine those two and we get 2. All right. Now, so we're just kind of separating, and the reason I did that, I wrote those, I could have written those all in the numerator. I just kind of separated them so we could see into multiples of fractions instead of just multiples of factors in the numerator. But what we can see right here is that we're going to get lots of canceling. And as you get more comfortable working with the ratio test, you might do that on your, combine my second and third steps here. You might combine those steps, but I'm just trying to show it to you all step by step here. So here, when we do this, we subtract the exponents, and this just becomes the absolute value of, we end up with just negative 10 to the first power times, now over here, when I look at these, the balance of the powers is in the denominator. There are more factors of 4 in the denominator, 2 more, because the difference here is 2. Or you could get 4 to the negative 2, and then that's going to drop down and become 1 over 4 squared. And then I'm going to pull, this guy doesn't even need to be in the absolute value anymore. N plus 1 over n plus 2 is positive. So n plus 1 over n plus 2. I could even pull that out. Now this is just a constant. And we can take the absolute value that becomes, that's the constant. Negative 10 over 16 in absolute value. So negative 10 over 16, of course, is 5/8. And that can come all the way out of the limit. It's just a constant, so that is just positive 5/8 times the limit as n is approaching infinity of n plus 1 over n plus 2, which is infinity over infinity. If we wanted to use L'Hopital's rule, we could. I don't even know if that's really necessary. That becomes infinity over infinity. But when we apply, yeah, sure, we could. There's lots of ways to do that actually. But we could apply L'Hopital's rule, still have that constant 5/8, and then we're just taking the limit as n is approaching infinity of 1 over 1, which of course is just 1, and that result becomes 5/8. So now what we have to do, based on our ratio test, we want to know if this L that we're finding from our ratio test, if that L is less than or greater than 1. If it is less than 1, we get absolute convergence. So let's take a look. It is, in fact, less than 1. So what that gives me is absolute convergence through the ratio test. So we can conclude, therefore, I'll squeeze it in up here because I'm running into some of my other examples. Therefore, the series that I'm looking at, the series of negative 10 to the nth over 4 to the 2n plus 1 times n plus 1, as n runs from 1 to infinity, converges, and we always want to say, right, we just justified it, but we always want to say why we're getting convergence. So this converges absolutely, not only that it converges, but what type of convergence? It converges absolutely by, and in this case, it was the ratio test. Now, the ratio and the root test, you can use RT as shorthand if you would like to use that. But when you're giving answers, we want to see all of the justification, right? We see the ratio right there. We show that the ratio ends up being less than 1. And then we discuss why is it that we got that absolute convergence, and it was through the ratio test. Okay, so let's take a look at another one. So we come across this one. We've got factorials. Factorials lend themselves really nicely to the ratio test. So I see this and I think, okay, I'm going to try ratio test on this guy. See what my result is. So If L equals the limit, we've got a k on the index here, so the limit is k is approaching infinity. And again, just remember with the ratio test, it is often a little easier to think of it in this form, where we take the k plus 1 term, so we plug in k plus 1, and then we multiply by the reciprocal, so we take the k plus 1 term, and we multiply by the reciprocal of the k term. So this is going to end up being our limit. Our L is going to be the limit as k approaches infinity. The k plus 1 term would be k plus 1 factorial over 5 to the k plus 1 times, and then the kth term, the reciprocal of the kth term, is going to be 5 to the k over k factorial. Now, of course, there's going to be some canceling here. Let's group things up a little bit. This is the limit as k is approaching infinity. We've got 5 to the k and 5 to the k plus 1. And k plus 1 factorial, I'm going to write it out. K plus 1 times k minus 1. Just remember how we define factorials. Factorials or bang, when the factorial, the exclamation mark, the factorial or the bang, k plus 1 bang, is going to be equal to k plus 1 factors where they descend by 1 each time. So k plus 1 times k minus 1, all the way down to 3 times 2 times 1. And k factorial is, of course, k times k minus 1, all the way down to 3, 2, and 1. Now, there is another way to think of this. When you think of k plus 1 factorial, because of the way factorials work, that is k plus 1 times k factorial. So we could also, you can see that right here in its expansion. Here is the k factorial, and here is the k plus 1 factor. So you could absolutely write it that way, and you could see that everything, all of the k factorial is going to cancel, because you have a k factorial on the top and a k factorial on the bottom. And this is going to become the limit as k is approaching infinity. Right here, all that's left is k plus 1 in the numerator. And here, when we do this reduction on the 5 to the k over 5 to the k plus 1, we get 5 to the negative first power, or 1 over 5. I'm going to write it as 1 over 5. And that is the limit as k is approaching infinity of, we can drop the absolute value, k plus 1 over 5, and as k approaches infinity, this is going to be infinity plus 1 over 5 is going to grow without bound. And that is clearly greater than 1. So if that is greater than 1, what that tells me is that this is diverging. This has to diverge. And it's absolute divergence here, right? We have k factorial over 5 to the k. Those are positive terms anyway. And so therefore, this guy from k equals 1 to infinity of k factorial over 5 to the k diverges by ratio test. Now we can say RT as well, but we definitely have divergence through the ratio test. Okay, let's look at another one. Let's look at this guy. So we have this expression raised to the kth power. Because that whole expression is raised to the kth power, I see that little kth power and I think, man, if I hit that with a 1 over k, right, if I took the kth root, that would undo that k power. And so this is just kind of a little thought bubble. This looks to me like maybe a root test is a good strategy to start with here. So let's think about doing the root test. So the root test says, let's define the limit L to be the limit, as in this case it's k approaches infinity, of the kth root of the a sub kth term. Of course, that is the same as saying taking the absolute value of the a sub kth term and raising it to the 1 over k. So we're going to go ahead and do that. Limit as k is approaching infinity, we're going to take the absolute value of 5k minus 3k cubed all over 7k cubed plus 2 to the kth power in absolute value, and we're raising that to the 1 over k. We're taking the kth root. Well, again, kind of the idea up here. Those will cancel, so k to the something to the kth power, when you take the kth root or raise it to the 1 over k, these will reduce down to 1, and then we're looking at just the limit as k is approaching infinity of the absolute value of 5k minus 3k cubed over 7k cubed plus 2. And in this scenario, of course, this becomes infinity over infinity. If we actually, it's negative infinity. Well, we have infinity minus infinity on the top. But we've got infinite behavior on the top, infinite behavior on the bottom. A few different ways to think of it, but I like looking at the highest power in the denominator and thinking about, let's try this algebra strategy rather than going to L'Hopital's rule. If we take, which of course we could do L'Hopital's rule, but I like using this algebra strategy. It'll be a little faster, I think, than L'Hopital's rule. So if we multiply by the highest power in the denominator there, 1 over k cubed, take that highest power and multiply top and bottom by 1 over k cubed, then this is going to become the limit as k is approaching infinity of the absolute value. We've got to distribute that to all the terms. So it becomes 5 over k squared minus 3. And in the bottom, 7 plus 2 over k cubed. Now we let k run to infinity. This is going to approach 0. This is going to approach 0. This is going to be the absolute value of negative 3/7, which of course is just 3/7, which is less than 1. And when we get a value out that is less than 1, we get absolute converges absolutely. And so we can say through this time it's through actually the root test. So therefore the series k equals 0 to infinity of 5k minus 3k cubed over 7k cubed plus 2 to the kth power converges absolutely by, in this case, it was actually the root test. Now, the root and the ratio test, it's obvious in the form that you did. Did you take the kth root or did you take a ratio? But we'll specify that there that we took the root test. And there's our result. Okay, let's look at another one. What if we have this guy? So this is the series from n equals 0 to infinity with a switch, negative 1 to the nth power over n squared plus 1. So if I try the ratio test on this, let's see what happens. So if L equals the limit as n approaches infinity of negative 1 to the n plus 1 over n plus 1 squared plus 1 times n squared plus 1 over negative 1 to the nth. Uh-oh, I'm seeing something kind of interesting happen here. Let's see what happens. We get negative 1 to the n plus 1 over negative 1 to the nth. We get n squared plus 1 in the denominator there. I'm going to expand that. I get n squared plus 2n plus 1 plus 1. So we get n squared plus 2n plus 2. And of course, when we take this ratio, we get just negative 1 on the top, but we're taking the absolute value of that. So that will be 1. And we've got n squared plus 1 over n squared plus 2n plus 2. And on this one, we could do the same strategy we did on the previous one, or we could take L'Hopital's rule, or we could just notice that the degree of p equals the degree of q. Since it's a rational function, it's going to be the ratio of those lead coefficients. And this result, I'm going kind of quick through this, but this result becomes 1, which this is the scenario where the ratio or the root test, if we get a 1 out of the limit, then the ratio or the root test is inconclusive. Okay, so what do we do, right? This is a good review of some other strategies. What I have to do is I have to try another test. So we try another approach. So just as a reminder, when we're testing for convergence now, we're classifying the type of convergence. And so the first thing I want to do when I'm testing convergence, let's first test the absolute value, because if I can get absolute convergence, I will be done. So let's take a look at what the absolute value. So we go through that. Anytime the ratio or the root test comes out as 1, then we're going to have to try something else, and we can practice our other techniques. So let's take the absolute value of negative 1 to the n over n squared plus 1 and consider that first. Now, when I take the absolute value, the switch goes away and it becomes 1 over n squared plus 1. And when I see that, I think, ooh, this is a good scenario for the comparison test. This looks, let's compare, use a comparison test. We have two of them, but let's compare to 1 over n squared. This looks almost like 1 over n squared. So what happens to 1 over n squared? Well, let's note 1 over n squared from n equals 0 to infinity converges by p series, where p equals 2, which is clearly greater than 1. So we're going to compare it to a converging series. We could use limit comparison or direct comparison here. Direct comparison is actually pretty easy to build. So let's practice that one on this one. So with the direct comparison test, what we do is we say, notice that n squared plus 1 is greater than n squared. Therefore, 1 over n squared plus 1 would be less than 1 over n squared. And of course, these are always greater than 0 for n greater than or equal to 0. We'll actually have to say just greater than 0. So for n greater than 0. And so definitely this series is smaller than this converging series. So we can say, therefore, by direct, use capital letters since it's a test, direct comparison test, also abbreviated DCT, the series 1 over n squared plus 1 from n equals 0 to infinity converges. Direct comparison test to 1 over n squared. Now, that's not actually the series we were looking at, though. Remember, our series has a negative 1 on it. So oops, let's undo that. Grab my highlighter. It didn't grab it. Our series has that negative 1 on it, but when we take the absolute value, we get convergence. So what that means, and the series with a negative 1 to the nth over n squared plus 1 from n equals 0 to infinity converges absolutely. All right. So that guy went through a couple of iterations of trying to figure out how to approach it and then applying rather than the ratio or the root test, because the ratio test came out inconclusive. We go to looking at, okay, well, if I can't use the ratio or the root test, let's go back and take a look at what's happening with the absolute value of the terms, and that set itself up nicely for a direct comparison test. And since the direct the series we were comparing it to in the direct comparison test converged, we had convergence, which means we have absolute convergence. This is quite a little pathway to our result there, but nice logical pathway looking at each of the steps and applying the appropriate test at the appropriate times. So that's a nice one to end on for this video, because it shows where that ratio or that root test becomes inconclusive and we go back and try something else, which is how we're going to want to attack series. When we look at a series to determine if it converges or diverges, we got to start somewhere. If the result we get is inconclusive, just like with integration, then we have to go back and try something else.